Hello everyone and welcome to the first lecture of Satellite Communication System Engineering. My name is Akram Al-Hourani and I will be your lecturer and course coordinator for this semester. Looking forward working with you. It is worth to sometimes remind ourselves with the benefits of the information age. This information age which is enabled by connectivity, by the internet, and also by satellite communication as part of this connectivity. For example, we could work from home because of the internet, because of this connectivity. We could connect things to the internet, such as sensors, agricultural sensors, transportation sensors. We could connect even a fridge or a washing machine to the internet. We can also have our economic interactions. We can send, receive money. Hardly I know anyone now visiting a physical bank branch. Everything is done online. We can also do self-learning. You can learn new stuff on the internet. I do that all the time. You can also do remote education, what we're doing at the moment, watching this lecture. You can also have remote and e-health. We don't have to visit physically the doctor. You can do e-government stuff. You can also read news and socialize. This is most people spending their time on this point. We can also watch cute cat videos. Sometimes we take it for granted that everyone got an internet. Well, it's not really the truth. If you look at this figure, which is taken from the United Nations report in 2020, and you can see different group of countries and the percentage of internet access. So you can here easily see that developed countries has a very high percentage of internet users. So you have 86% of the populations are internet users. However, if you look at an example here on the developing countries, you can see that this figure drops dramatically to about 50%. Now, even if you look at this last bar here, which is the least developed countries, what you can find, the internet access is only 19%. So 80% of the population, they don't have internet access. Now, if you have a zoom in detail, and these details I took from the International Telecommunication Union, what you can find, there's even more difference between rural areas in least developing countries and urbanized areas. So if you look at rural areas versus urbanized areas, you see there's a vast difference. And you might ask yourself immediately, what is the reason that rural areas do not have proper coverage? Well, because you need infrastructure, you need optical fibers, you need to lay fibers in order to connect to these houses. How satellite can help us in bridging this gap? Well, of course it can, because satellite does not require wires on the ground. It can provide coverage directly from space. So what are the main benefits of satellite communications? But the first thing is the ability to provide a global coverage. That is, you can provide remote regions, a top of a mountain or a rural area that is very hard to connect through an optical fiber cable. You can also cover ships sailing in the sea, vessels. You can cover aircrafts. Of course, these things you cannot cover them by an optical fiber, and they have to be, our satellite is one of the main solutions to provide internet for such applications. Now, in the case of, or the unfortunate case of a natural disaster, say you had an earthquake, and this earthquake destroyed the infrastructure, destroyed the power line, or destroyed the telecommunication tower. Satellite is a very rapid, very fast solution that people can use during the recovery operation. The third is to have a global and a low latency coverage. So when I say low latency, there is a new research or a new prospect that satellites can be interconnected to each other. We will see that in more details in upcoming lectures. When satellites talking to each other, rather than talking through Earth, they might deliver your message faster than if you are sending your message through a fiber. Why is that? Because the signal in free space travels at the speed of light, while the signal in optical fibers travels at less than the speed of light. Now, this is not yet happening, so intersatellite connectivity is not yet a widespread thing, it's experimental. We will talk about that in more details in the upcoming lectures. Defense uses communications heavily because it's very flexible and you can deploy troops remotely. The other thing is, it's a futuristic point, you can use satellite communication for the science and exploration. You can connect Mars rovers through satellites. You can connect even moon. If you want to have a moon colony, for example, in the future, you can connect that through satellite communications. So what will you benefit from this course? Well, first you will learn a lot of new stuff about new technologies and about satellite communications. It will also give you a very good boost in your career if it happened to work in something related to satellite communication. You don't have to be a satellite engineer, but if you work in anything related to that requires satellite, you will be an expert or a good starting expert in this matter. So the first thing is you could work as a payload designer. You can design an actual payload that will go in space. That's very exciting. You can do integration of satellite communication into a network. For example, let's say you are managing a large terrestrial network and then you need a remote connectivity to a remote office. You can use satellite connection, and then you understand about that because of this course. Also, you could do planning, satellite network planning. This is not an easy task. I know a lot of people doing that. You can also start your own company that will do satellite communication. Now, if you do a bit of search in job offering websites, you'll find there are a lot of jobs related to satellite communication. So this was a recent search I did. And you can see here there is an embedded system engineer that is to design the microcontrollers, the components of a satellite. And there's a focus on the communication side. There is also an IoT, Internet of Things over satellite. There are also requirements for gateway technician. I also went to, for example, a SpaceX website. I found many jobs, very interesting jobs, all about communication engineering and communication system engineering. So what background is preferred for this course? One thing, MATLAB. I would start with this. If MATLAB is a new word for you or you haven't done any exercises on MATLAB, now you don't have to be an expert in MATLAB, but if this is something really new to you, I suggest to go, for example, to this link, have some basic exercises on how to plot different functions and then how to manipulate matrices, etc. You also need to understand a bit of statistics such as histograms, probability density functions, cumulative distribution functions, what is the mean, what is the standard deviation, etc. Knowing digital modulation is also very good. So if you understand what's a QAM, QPSK, what is the meaning of coding, etc. Also, some understanding of the noise process and what is the meaning, for example, of a signal to noise ratio. Let's start with some recent exciting examples what's happening at the moment in satellite communication industry. So there are two big names I can recall now. For example, you have the Starlink from SpaceX. So these are terminals, I've seen them even in the city. So these are satellite antennas. They are patch antennas. So this one has a near global coverage. And at the moment, I think they have more than 6,000 satellites. Speed is expected to be between 50 to 200 megabits per second. Another company, this company we worked a lot with as a research. We have other videos covering that as well if you're interested to know what was our work between RMIT and OneWeb. It has a global coverage. Also, it has a staggering number of satellites. So I did actually go ahead and extract the two-line elements which describe the orbits of both constellations. So what you can see on the left-hand side is the OneWeb constellation. At this date, there were 636 satellites. And on the right-hand side is the Starlink, which has a around 4,000 satellites at the time of doing the simulation. Now, you will learn in this course how to do this plotting by yourself, as we will see in the upcoming lectures. Always check the syllabus on Canvas for any updates in the course structure. However, what we will do in this first lecture, we are going to cover the course outline. We are talking in general about satellite communication system, and we'll talk a bit about the architectures. In the second week, we will cover the coordinate system. We will learn how to convert between different coordinate systems, very important. We'll learn how to establish orbits, satellite orbits, and what are the different parameters that describes its orbit. We'll also learn how to simulate these orbits. You will do some nice plotting as the two graphs you saw there in the previous slides. In the week 3, we will also analyze the satellite visibility. Low Earth orbit satellites, which are closer to Earth, are not always visible. They will come and go, and we will learn how to estimate the passes when the satellites are available. We will also study some aspects of the satellite antennas. The fourth week, we'll cover the satellite link budget, very important topic in satellite communication. And then we'll talk about satellite radio channel, how the signal propagates between satellites and ground terminals. We will have the mid-semester assessment in week 6, so there will be no formal lecture here. Week 7 will cover in-depth digital modulation in satellite communications. And then after that, we will have the performance. We'll study the performance of these communication techniques, which is the bit error rate, BER, and what is the impact of coding on the BER. Week 9, we'll study multiple access. If you have multiple users, how will these users access the satellite? We'll try to have an invited industry lecture. And then week 11, we'll talk about satellite networks. We'll move to layer 3. So most of the course is in layer 1 and layer 2. Layer 3 will be covered in this lecture. We'll have 3 labs. The first lab will last over 4 weeks and will cover the satellite coordinates, the orbits, and how to generate the orbits, the geometry. The second lab will cover the link design and analysis, and also will run for 4 weeks. The last lab will run for 3 weeks, and you will have hands-on on hardware to emulate an end-to-end satellite connection. Most of the labs will be conducted using MATLAB, and also we'll use software-defined radios, as you can see here in this picture. The labs, each lab worth about 10%, and the lab will be in groups or individuals, so you can be 1 or 2 students per group. There are 4 assessment tasks in this course. The first task is the mid-semester assessment, which will have 20% mark. This one will cover approximately half of the course and will be a combination of problem solving, multiple choice questions, some short essay answers. I will jump to assessment task 4, which is the lab reports and performance in the lab. This is 30% in total. So I said you will have 3 lab tasks, each task worth 10%. The third assessment task, which is the project assignment, this is a very important assignment, and I advise students to start working on that as early as possible. This way, 30% of the total mark. This will try to replicate what we will do in real life in an industry, and will focus on the design and simulation of a satellite communication system. The second assessment task is the end of semester assessment, which will be very similar to the mid-semester assessment. This is 20% mark. We have here some terminology that we need to learn about satellite communication. So the first terminology is ground segment. Ground segment involves everything on the ground, including the user terminals, which are the users accessing the internet via a satellite or an antenna, and this antenna is connected to a modem. The modem is connected to a laptop or a company. We also have gateways. These can consider as the aggregation point where all these user terminals are connected. The gateway is connected as to the main internet, to the fiber network. We also have the space segment, which includes satellites. It might include inter-satellite connectivity, so satellites might be connected to each other. We also have something called the control segment, which is around controlling and monitoring the health of the entire network. Now also you need to get familiar a bit with the terminology of link. The connection between the users towards the satellite is called the uplink. It's called from here upward to the satellite, and the connection from the satellite to the ground is called the downlink. Now, both connections, uplink and downlink, which are between the user terminal and the satellite, is called the user link because it's connecting the users. The other link is called the feeder link, which connects the satellite to the gateway. So again, the gateway is the one that aggregates the traffic coming from the users. A satellite footprint is the region where the satellite can provide a service. This is an example of a certain satellite which is targeting mainly Australia and New Zealand. And what you can see here, different contours. These contours shows the equivalent isotropic radiated power, or the equivalent amount of transmitted power by the satellite at different locations in Australia. Now, modern satellites can reconfigure their coverage plot. So you can, if you have more customers in another country or some island, you can reconfigure that so you can cover that island. We will cover this concept in much more details in the upcoming lecture. The figure on the right-hand side shows you an example of a traditional satellite configuration. Basically, these traditional satellites are just simple repeaters. They take an analog signal from the ground, amplify the signal, and transmit it back to the ground. So let's have a look here. So we have the signal arriving at the antenna. So here's the antenna. The antenna transmits the signal to an amplifier. And this, what happened here, you have different bandpass filters, and, each bandpass filter is attached to an amplifier. And this bandpass filter is attached to an amplifier, and the amplifier transmits the signal to an amplifier, and the amplifier transmits the signal to an amplifier, and the amplifier transmits the signal to an amplifier, and the amplifier transmits the signal to an amplifier, and the amplifier transmits the signal to an amplifier, and the amplifier transmits the signal to an amplifier, and the amplifier transmits the signal to an amplifier, and the amplifier transmits the signal to an amplifier, and the amplifier transmits the signal to an amplifier, and the amplifier transmits the signal to an amplifier, and the amplifier transmits the signal to an amplifier, and the amplifier transmits the signal to an amplifier, and the amplifier transmits the signal to an amplifier, and the amplifier transmits the signal to an amplifier, and the amplifier transmits the signal to an amplifier, and the amplifier transmits the signal to an amplifier, and the amplifier transmits the signal to an amplifier, and the This amplifier takes the signal amplified, you combine all the signals, and then retransmit them back to Earth. Now the reason you don't have just one amplifier is because of the power limitation of a single amplifier. You need to have more power, so that's why you're dividing the bandwidth into different sections. Now again, this is a traditional satellite. It's also called bent pipe. It's a nice name because it's like a pipe you send and you just receive back. There is no switching capabilities, there is no decoding capabilities. It's not even capable to detect what type of traffic being transported. You saw an example in previous slides how whole Australia was covered in a single beam. So that means a user within Australia transmits a signal towards the satellite takes the signal and transmits it back to the entire region. Now, if your receiving station is within that region, that means your receiving station will receive your signal. However, what happens is that you are occupying a bandwidth, a channel for the entire region in whole Australia. No one in this can use your frequency because you are using it. To solve this matter, there are new satellites, also called high throughput satellites, which employ multiple beams. So that means you can use set of frequencies here. Let's say you can use frequency 1 and frequency 2 and frequency 3, and you cannot reuse these at this spot, but if you go further, you can use again these frequencies. What does that mean? It is similar to the cellular concept. If you studied that in the past, it means that these satellites can have more spectral efficiency and thus achieve higher throughput. They are faster in transmitting data. These are called multi-beam satellites, and typically you can reconfigure these beams and orient them towards users. More advanced satellites are called regenerative satellites. And what do? They take the signal, amplify it, demodulate it, and do signal processing. They recover the data and then do modulation again and send it back to Earth. Now you will find that this architecture is much more advanced than the bent pipe architecture because you can regenerate the data. That's why it's called regenerative. You can regenerate the data and thus have much higher fidelity, and that means lower bit error rate when you transmit through a regenerative satellite design. These are also some terminologies related to the orbits. So we have the low Earth orbit, or LEO. LEO have a small coverage usually, and they are at small altitude. Now, some examples of using LEOs are the two large constellations, which are Starlink and OneWeb, as we saw in the previous slides. We have also MEO, which are called medium Earth orbit. Examples of MEO are the global navigation satellite systems, such as GPS system and Galileo. So these are in the MEO orbit. So each satellite passes for a few hours. LEO satellites can pass only for 15 minutes or even less in some cases. We will see that in details in the upcoming slides. Now we also have an orbit called GEO. Now the GEO orbit rotates with Earth rotation, so it appears stationary. It doesn't move. So if you have an antenna pointed towards the satellite, you don't move the antenna. It's always pointing towards that satellite. As you saw in the previous slide, low Earth orbit satellites have very small coverage area. So if you want to provide a global coverage, you need to have multiple satellites. Satellites are usually designed in a constellation, which is a group of satellites providing the service. Examples you saw again in the previous slides for SpaceX and OneWeb. And these configurations, these are non-configuration. OneWeb is using a configuration called Walker Star, which is the one on the right hand side, and Starlink using a configuration called Walker Delta, which is shown on the left side. Also, constellations such as GPS and Galileo uses something similar to the Walker Delta constellation. Here is an example of a Walker Star configuration. So this is simulated using MATLAB. So what you can see here, the different satellites, and each satellite has a certain coverage area. And as the time of simulation progresses, you can see the satellites are not fixed with respect to users. Now the Earth, if you pay attention, is also rotating in this simulation. Let's have a closer look at how a satellite terminal looks like. A satellite terminal will have an antenna to receive the signal. The signal is passed through a low noise block down converter. So you're basically taking the satellite frequency, which is typically in the C, Ku, Ka band. So we're talking about something between 5 gigahertz to about 20 or 30 gigahertz. It's very high frequency, and you can't send this directly in a cable. So you have to amplify it first, down convert it to around 1 gigahertz. So it can easily go through a cable. So this is a coaxial cable, and this coaxial cable is connected to a demodulator, which extract the signal and send it to the user. Now the user data, when you're transmitting, it goes through a modulator, it goes through another cable, go to a block up converter, which take the signal in the 1 gigahertz region and convert it towards the C or Ku or Ka band, depending on the satellite you're using, and being transmitted back to the satellite. Of course, there's a power supply and management system to the indoor units. Now, typically, you have an indoor unit and outdoor unit for a satellite terminal. Now, some new terminals, they have only an outdoor unit, which has everything inside it, and you only need to connect it with an Ethernet cable or with a power over Ethernet cable. These new kind of terminals are much easier than the older types. This is an example of a traditional satellite terminal. I have installed this terminal myself a long time ago. So what you can see here, you can see the reflector, the antenna, this dish people call it. You will see the feeder. There's a small here, it's called the horn antenna, this little thing. And you will find here an LNB, which take the signal and amplify it and down convert it. This cable is an IF cable, which is intermediate frequency, takes the signal which is coming in the Ku band for this particular application and transmit it back into L band, which is around 1 gigahertz. Now what happened, the signal goes to the inside, so it was connecting a cellular site. What you can see here is the buck or the block up converter, which takes the transmitted signal, amplifies it, and transmit it to the reflector. Reflector send it to the satellite. Now, newer terminals are much smaller because they're using higher frequency. When you use higher frequency, you can afford smaller antennas because the gain will be much higher for these frequencies. We will have much more detailed discussion on the antenna design and link design in the upcoming lectures. On the other hand, gateways are typically much larger than user terminals. They employ higher RF radio frequency amplifiers. As such, the total EIRP, which is the equivalent isotropic radiated power, is much larger for a gateway. This will enhance the reception of the signal, having a large antenna, and also the uplink power would be much higher. The EIRP power would be much higher. This will guarantee a much better link in both the uplink and the downlink. Now, because you have a large antenna, the beam width of the antenna becomes much smaller, and as such you require tracking. So even for a geostationary orbit, so geostationary orbit, we talked about it before, and this satellite in this orbit appears as if it is constant in the sky. So typically for a normal terminal, you don't need to track the satellite because it appears constant. However, this is not really constant. It has some movement, apparent movement with respect to the ground. So for large antennas, which have a very narrow beam width, require tracking. So you'll find here there are two motors, one for the elevation, controls how high is the antenna, and one for the azimuth, controls the rotation around the axis. So these two motors will point the antenna, or will ensure it's always pointed correctly toward the satellite. Now also mind that the satellite does not have necessarily to be a GEO. It could be also a LEO satellite, and in this sense you have to have tracking as well, because the satellite just passes, and during it pass you have to keep track of it. Let's talk about a very important topic, which is the radio spectrum for satellite communication. So what you can see here, the horizontal axis is frequency in gigahertz, and these frequencies are designated with different letters. Now this convention of letters is applicable to satellite and other as well applications, but the way you will find that there are slight differences in the definition of the bands depending on the application. But for the satellite, this is the most accurate designation that I'm showing you at the moment. The first lowest frequency what we can find is the L band, which is around 1 gigahertz. This frequency you will find is used for land mobile applications. So these are the satellite mobiles that are connected directly to the satellite. Also, this is the frequency of applications in GNSS, like the GPS system, the GLONASS and the Galileo, the Baidu. All these are called the GNSS, and they help you to find your location on Earth. The other system, which is called the S-band, some telecommunication and radar uses the S-band. The C-band, this is for old communication. This is between 4 and 8 gigahertz, and this is direct to home TV. Require a very large antenna, by the way. The Ku band, this is the older kind of connection between satellite and users. It's used also for direct to home TV and for communication. Now, Ka band is the newer band used by most of the newer players in satellite communication, such as SpaceX and OneWeb. Higher frequencies as Q and V band are much harder to communicate over because they incur much more attenuation. Now I'm going to show you here some animation. So as say, this is the Ka band, and it's very nice because it has very small antennas. You can see it is an example of a SpaceX antenna, and these are very occupied, these bands, and that's why new operators are trying to explore new bands, which is considered as a treasure at the moment because it's quite empty. But again, it's very hard to use these bands. There are different satellite services out there. So the fixed satellite service is the traditional satellite that is fixed in its position and is providing coverage to a fixed user. That's called fixed satellite service. We have the high throughput satellite service, which is also a fixed satellite service, but provides multiple beam. We covered that in a previous slide. So here, you typically have a single beam, and here you have multiple beams. And we said in multiple beams, you can reuse the frequency and thus provide much higher throughput. We have the new mega satellite constellations or mega satellite networks, which I show you examples of OneWeb and Starlink. And also we have applications with this Internet of Things over satellite when you want to connect small sensors or track different assets, for example, from space. These typically do not require large bandwidth and are also delay tolerant, so you don't have to worry about delivering the packet immediately. Now what you can see here, there is a comparison. You can look at it between the data rate, latency, global availability, the energy consumption, and the spectral efficiency. For example, let's look at the mega satellite networks and compare them to other applications. So mega satellite networks are expected to have very low latency if they are enabled with inter-satellite connection when you compare them, for example, to IoT over satellite or other services. Now, fixed satellite services are typically in the geo orbit, so you'll find they're not really performing quite well in terms of the latency. But even if there is no internet satellite connection, the satellite itself is much closer in the mega satellite constellation because it uses LEO orbit. So LEO orbit is much closer to Earth, and as such it has much better performance in terms of latency. So more here means better performance, means lower latency. So this arrow means lower latency. And as we saw here, as we said here is a geo orbit. Geo orbit is farther, and thus the signal requires more time to travel to the satellite and back to Earth. Now, in terms of global availability, you will find that fixed satellite services covers a certain geographic area, so they do not provide a global coverage, while mega satellite constellation aims to provide a global coverage all around the world. And so on, you can have a look at the different other parameters. We'll dive into more depth into these different types of satellites. So the fixed satellite services usually have a single beam. For example, this satellite, this entire region is covering all Europe and more, and a bit of North Africa. So if a user within this region, so here's a user, transmits a signal, the satellite takes the signal and transmits it back to the entire continent. So if you're using some frequency, let's say some 4.1 gigahertz, for example, your frequency is allocated to you, and let's say you are somewhere here, but the entire region cannot reuse your frequency because it has been allocated to you as a user. That's a quite waste of resources. Typically, satellites in the fixed satellite services employs the bent pipe architecture, which we discussed previously. Means any signal comes to the satellite, it's just an analog repeater. It's being transmitted back to the entire region. On the other hand, high-throughput satellites employ more than one spot, typically tens of spots. And you can see here what I did. I plotted it is not a real satellite, that's a simulated satellite, showing if I'm reusing the spectral resources. So you can see here that I have three colors. We have red, blue, and green. And what I'm doing here, I'm reusing the frequencies at every spot. So for example, if a spot green is using certain set of frequencies, I can reuse these frequencies in the next green spot. And when you reuse the frequencies, what happens is that you can increase the bandwidth of the satellite. You can reach much higher throughput. Now mind, both high throughput satellites and fixed satellite services are stationed on the GEO orbit, which is around 35,000 kilometers. The minimum delay, so that's the round trip delay, which is going from the terminal to the satellite and back from the satellite to the ground, require 238 milliseconds minimum. That is meaning this is the satellite subpoint. This is the point exactly under the satellite. It has such a delay. But for points which are a bit veered to left or the right will require more delay than that. Now mind that this delay for a voice application might not be a problem, but for data applications which are typically using TCP/IP, you might have some problems with the protocol. And also for industry and control applications, having a delay of a second or half a second, in this case a quarter second, but if you count the delays of the routers and delay of other elements, this can be up to half a second. So controlling things remotely by a satellite become a bit problematic for in GEO orbits. Mega satellite networks are the new satellite constellation type. We gave an example of SpaceX and OneWeb. This is a simulated constellation. This is a Walker star constellation, it's called. So what we will find, a vast numbers of satellites, hundreds or even thousands of satellites. These are much closer to the ground, such that the delay between the terminal and the satellites is much smaller. Also, the satellites are having much smaller footprint. You can see the cover spot is much smaller. And then also you can reuse the frequencies in different satellites. Even some satellites have multiple spots, so you have way much higher spectral efficiency. That means the link will be faster. Also require much lower power because the satellite is closer, so there's a lower free space path loss. And the terminals makes the terminals, mean the antennas that will be shipped to the user, much smaller and much more economical. Also, the launching cost of such orbits are much less than GEO orbit, obviously because it's the lowest distance. And as said previously, if these satellites are interconnected by inter-satellite links, there is a potential for having faster than fiber connectivity. And I'm putting here the figure. The connection between two satellites will be at the speed of light. The signal will travel at the speed of light. However, the connection via a fiber, which is on the ground, will only travel at 0.67% of the speed of light. However, till today, the inter-satellite connection is not yet widely spread. There are experimental satellites. Some new constellations, they are promising to have inter-satellite connection, but it's not yet, as of today, not yet widely spread. Let's have a closer look at the architecture of mega satellite constellation. Just a very simplified architecture. So as said, we don't have at the moment connection between satellites. So this connection is called the inter-satellite link. And this is typically employs laser, as we call it also free space optics or wireless optical communication, or higher frequencies such as terahertz, also could be in the microwave region. Now, at the moment, user terminals transmit to the satellite relays back to the nearest gateway. Now, these are typically low Earth orbit satellites. So these are in the LEO orbit. So let's take an example. Suppose you have the map of Australia, and in Australia you might have, for example, 3 or 4 gateways. If a satellite passes, here's a satellite passing, and you have a user, so here's the satellite, and here's the user is transmitting toward the satellite is relaying back the signal to the closest gateway. Now the gateway is typically connected to a very high bandwidth fiber optic network, so it's connected back to the internet. And we saw here so this is the internet connection. We also said before that you have the link between the user and the satellite, we call it the user link. The connection between the satellite and the gateway, we call it the feeder link. Internet of Things, or things that are going to be connected to the network, such as sensors, such as monitoring equipments, transportation, asset tracking, agriculture, smart cities. All these sensors can be connected, or typically are connected, through terrestrial networks. But for remote regions, it is hard to provide coverage in remote areas. So it would be suitable to use a satellite for connecting such remote regions. And this is an example, this is an estimation that will be about 30 billion, or even more. I saw some estimation of these IoT devices, and a lot of them will be in remote regions. So it would make a lot of sense to use satellites to provide coverage for these Internet of Things devices. Now mind, if you had the course before, wireless sensor network and IoT, that these IoT devices are quite different than the typical users, because typical human user or typical internet user. And the reason is that they require much lower bandwidth, and also they are much more numerous. So you can see in billions their numbers. So they require much special treatments. And typically at the moment, IoT satellites are different than the satellite provide broadband services to typical users. These are two examples of IoT networks. So the one on the left-hand side is an Australian company, and you can see here they have a few satellites, and these satellites are in the LEO orbit. So they are not providing a continuous coverage. For example, for Australia, a terminal would require to wait, for example, a few hours, depending on the number of satellites, to transmit its packet. So these are LEO orbits. On the right-hand side, this is an international company called Inmarsat, and it's providing coverage through a geo orbit. Now you can see the satellites are not really moving. So what I'm doing here, we are moving with the Earth. So, and the satellites are fixed with respect to Earth. So these are in the geostationary orbits. So if you're interested in the recent trends in satellite communication and in machine learning on satellite communication, please refer to this paper. You can use machine learning in satellite communication for many aspects. You can forecast the radio channel. As we saw previously, radio channel in the Q and V band is quite unstable and requires some special treatment to be used. One of the solutions is to use machine learning to predict that. Inter-satellite connection is a very interesting topic. As well, you can optimize the connections using machine learning. You can also share radio spectrum. So these are all advanced topics for research. You can share the radio spectrum. You can use machine learning to improve the effectiveness of sharing radio spectrum between satellites and between different operators. And there are many other aspects that machine learning can benefit satellite communication. This is another example. This is one of the world's largest beamforming antenna. So you can, if you zoomed in here, you can find that each of these circular patches is actually an antenna. And by changing the phases between these antenna, you can orient the coverage. You can form different spots. You don't have to physically steer the antenna. Rather, just change the electric phase, and you can steer the coverage toward different users. So this particular satellite aims to provide 6G and 5G towards mobile user directly to your mobile phone. You don't need to buy any specialized equipment. You just use your mobile phone directly towards the satellite. These are some of the trends are currently going for satellite communication. Here is a summary of the lecture. We covered the importance of satellite communication and how they are playing a pivotal role in providing coverage for remote regions and during disaster, and for areas that it's impossible to connect by fiber, such as air and sea. We also saw the types of different orbits and few constellation types. We saw the Walker Delta and Walker Star constellation. We looked at different architectures. We looked at the bent pipe architecture and the regenerative architecture. We said the regenerative is much better. We also look at the new trends in satellite communication, such as the direct 5G and 6G and IoT over satellite. Finally, I hope you have enjoyed the first lecture in satellite communication systems. In the upcoming lectures, we will dive in much more technical details. We'll see you soon. Take care.